So okay, I was told it should be elementary, and of course I think if I talk, it's always elementary, but some people think different. So I made the introduction. Well, Diophantine geometry has a long history. Usually you think it's the first occurrence are the old Egyptians who needed to construct right angles to make measurements, and they knew that if you have a triangle with lengths 3, 4, and 5, then it has a right angle. Okay, so I should talk about algebraic variety. They are defined by algebraic equation. So you don't have sines or cosines, but you have polynomials, and I wrote some down here. So the general theory says that there are so-called affine varieties, and they are given by commutative rings. So if you look at the convolutions of some polynomials fi, then you can take the polynomial ring divided by the ideal generated by the fi, and then the points of this variety in any ring are the homomorphism into the ring. So an example, maybe the simplest example is a circle. Well, I should say, I mean, usually you talk about the real points, because the complex points that would need twice the dimensions, and our thinking is mostly limited to 2 or 3 dimensions, and it's, for example, difficult to show things in higher dimensions. And so if you take the equation x squared plus y squared equal 1, then that's a circle, as you should have learned in school. And and the circle is a so-called curve of genus 0. And for genus 0, it's easy to find the rational point. Either there's none of them, which is very easy to find, or they are parameterized by one parameter. And for the curve, for the circle, maybe I can use a blackboard, or do you have chalk here? Yeah. Here. Okay, you have a circle. This is supposed to be a circle, and well, and you have a point -1, 0, or 1, 0. Okay, and then the procedure is to parameterize the point. Use the fact if you have a line through the circle, it will meet it in 2 points in general, because the 2 points are given by by a quadratic equation, and there's usually 2 solutions. It's something and plus minus the square root of something. And then if you already know that one of the points has rational coordinates, then the other one must have rational coordinates too, because if a plus square root of b is rational, then a minus square root of b is 2. And so you take one point, let's say this one, which is rational, and then you look at through all the lines through the circle, and they are given by some slope t. Which is a rational number, and then the second point is also a rational solution. And when I made the notes, I figured out what these are. So it's a point with coordinates 2t or 1 plus t squared and 1 minus t squared or t squared minus 1. I hope I wrote this correctly. Yeah. So this is if you do geometry and you look at the equation here, and then you have a slope t, and then you get this second point. And so this means all points, rational points on the circle, can be given by a parameter t, and they're then given, the coordinates then are given by those two equations. And there's so degenerate cases. If t would be infinity, you would have a tangent here, and then you would have a sort of this point counted twice. Well, okay. And so for the circle, you can parameterize all points. And for example, for t equal 2, you get 0.45 and 3/5. This. And this gives you the standard rectangle triangle with sides 3, 4, and 5. And so this is how the Egyptians figured this out, and they used this for measuring. After the yearly flood, they had to rearrange things. Well, one point is this picture is misleading. These are the real points, but we should look at the complex points. But then this is more difficulty, because the real points lie in the two-dimensional plane, and the complex point would have to lie in the complex two-dimensional plane, which is four-dimensional. And so even here you have only three dimension, and maybe you can take the time as a fourth dimension, but it's difficult. And also usually you have to add points at infinity, while these are talked about affine varieties. But really, if you don't have points at infinity, you are missing some points. And for example, if you have two parallel lines, then they won't intersect at the finite level, but at infinity they will intersect. And well, and the easiest, well, I said this was had a curve of genus 0, and after the 0 there's 1. Well, the genus is a topological invariant, and the simplest example are the elliptic curves. They are called elliptic curves not because they are ellipses, but because the corresponding integrals allow you to compute the length of an ellipse. And so they came, and the easiest one is this, you take the square root of a cubic polynomial, well, which is a little bit cheating, because you have to add infinity, but how do you get this? How does the curve look like? Let's say you have the equation. Then, well, I mean, let's say x is in the complex plane, or well, there you add a point at infinity. So the complex plane is just a plane, as the name shows, but if you add a point at infinity, it becomes a sphere. Well, and then what are the points, how do the complex points look like? For the most x, this is non-zero, and you have two solutions of this. So over a point in the x-plane, you have 2 points, but for the zeros of this one, you have only 1 point. So you have sort of 2 copies which map to this. You take the positive root and the negative root, let's say, and then you have 2 copies, and over this exceptional point, and there will also be an exception infinity, you have only 1 point. But you get into difficulty with this, because if you look at C, you have the points and maybe I write infinity here. You have 4 points on the sphere, and over each point you have 2 points above, but over those 4 called ramification points, you have only 1. And well, but it's even more complicated because you march on a small circle around one of those points and deform continuously the root. Then you come from the positive root to the negative root. So these things are more complicated. And well, I mean, this would not be Abel or it would be Riemann. You can do this. You take your slice, your plane along on the path between 2 ramification points. So then you have a sphere and you have 2 slices in there. Then you widen them, and so it's a sphere with 2 holes, and then you glue these 2 together, and then, well, you glue the lower side on one to the upper side on the other one, and so on. And then you can figure out if you work that this is a torus. I mean, you have those two spheres which are connected. Well, it helps in this if you already know what is supposed to come out. Okay, and then this is called a curve of genus 1. And if you have more zeros here, you get higher genus 1, 2 or so. And the point is the curves of genus 1, they have a group structure. If you have 2 points, you can add them for some rule. And so they form algebraic groups. And and it was it was the edge of research at Abel's time. You have the so-called integrals, where I can write this as the x over y. And if you want to do integrals, there are various tricks like substitutions and so, but for these integrals, none of them work. And then it was Abel and competitors which found you shouldn't consider this as a function. You should look at the inverse function, and then it will be a double periodic function. And and the elliptic curve, what Mordell did, if you have an elliptic curve over a number field, you can look at the points over the number field, and they form a group because the elliptic curve is a group. And then the fact is that over a number field, it will be a finite degenerated abelian group. And this is, okay, I mean these things, but in cryptography and so on, it plays a role. And then he asked, if you go to higher genus, or genus 2 or 3, what happens there? And he said, it might be that there are only finitely many solutions, and he saw no reason why this would be wrong. So this was Mordell's conjecture, which was then in the world. I have a chance to mention Abel again. I said for curves of genus 1, they are an algebraic group. For higher genus, there exists also a group, but it's not the curve itself, but it's the so-called Jacobian. So Jacobi was a competitor of Abel, and it is higher dimension, but these things are now called Abelian varieties. Well, and under Weil in 1928 generalized Mordell Theorem to the fact that the rational points of a number field form still a finitely generated group. And well, in the proof, one uses so-called heights. A height of a rational number can be a quotient of two numbers can be defined as a sum of the absolute values of the denominator and nominator. It shows, the important point is the height sort of gives you the complexity of a point. And the main property is that if you bound the height above, there are only finitely many points. And usually, height functions, people don't want to know too much about them. Want to have the precise value. They only want this property. Okay. So I introduce heights. Well, and then, you had the Weil theorem that the rational points on the Jacobian form a finitely generated group, and the curve lies in there, and then the natural way was to prove Mordell's conjecture was to try that I sort of have this finitely generated group, but it avoids most point on the curve. And this was tried later, but it's only in around 1990 that Vojta find a proof for this one. But anyway, there were for Diophantine equation, there was a new thing invented by Diophantine approximation, which is usually associated with three names: Thue-Siegel-Roth, and fortunately Thue is a Norwegian, so I can say this here. And he invented the method. Siegel was a German who proved the main application, and Roth, well, the nationality is complicated. He perfected the method. Well, and I'll give you, because it's invented by Norwegian, I'll give you an example how this works. Let's say if you have a polynomial of degree 4 with integer coefficients, then you want to show that the equation fxy is 1 has only finitely many solutions. And well, and the idea is if you have a solution x over y, then you write f of xy as the product of these things. And one of the factors might be small, because x, well, at most one of the factors would be small, because otherwise you have different equations, and the factors usually have the size, the height to some power. But the height have the size, the height of x over y, and only for one point they may be small, but there's Roth's theorem, and which says that it's only at most the height, at least the height to the minus 2, and then if you do this together, you get that the value of fxy is power of the height, and if you want this value to be 1, then the height has to be bounded, and there are only finitely many solution. So the Norwegians were clever people, even then. Well, and maybe I give whether I should say too much about the, in Roth's, Roth did this in the 50s, and if you have a good approximation of an algebraic number, and you have several of them, you choose, there are infinitely many of them, you choose them that the heights strongly increase, and then find a function, auxiliary function, and then, which vanishes to higher order at these points, and then you have to find a contradiction, which is called Roth's lemma, and it's complicated. So this was the final thing by Roth, and before that, there were easier arguments with two factors. Okay, now we go ahead in time, and in the 1960s, this was an important time. So there was Igor Shafarevich, which gave a talk at the ICM in Stockholm in 1962. Igor Shafarevich is a Russian mathematician, and he also occurs in Solzhenitsyn's work. And and he said something about curves with bed reduction. So bed reduction means the following. Let's say you take the square root of a polynomial, and in general this is non-singular if the polynomial has no multiple roots. But this is true over Q, let's say. But then if you have integral coefficient and you reduce modulo prime p, then it may be true that two roots start to coincide. And this is supposed to be a point of bed reduction. It usually means that the prime p divides the discriminant, and there are only finitely many points of bed reduction. And Shafarevich made the conjecture that if you take curves of given genus and given set of bed reduction, there are only finitely many. And also a Mordell, there was progress. There was Manin, who did a proof in 1963, which gave us the Gauss-Manin connection, and there was a proof by Grauert. They were over function fields. Well, function fields are fields like, say, Q of x. And they are related to curves over, so they are related to curves. And then if you have a curve over a function field, that the surface. So see. And you want to say something about this, and you want to prove that there are only finitely many rational points, meaning that there are only finitely many sections. And this cannot be true in general, because if you have constant surfaces, so you have a product of B with some curve C, then you get the constant points in C, and there can be infinitely many, so you have to exclude them, and this is called, the bed curves are called isotrivial curves. And then Parshin proved the Mordell. And it's known that Shafarevich conjecture implies the Mordell conjecture, This is the so-called Parshin construction. If you have a curve and a rational point, you can construct a new curve which is covering only ramified at this point. And so you get from points to curve. And then in 1968, Parshin proved Mordell and Shafarevich for curves of a function field with everywhere good reduction. Well, I mean, and the idea was, well, they proved that sort of sections are parameterized by an algebraic variety, which means in this case the important point is quasi-compact, so it's not too big. And then they show rigidity, which means that the algebraic variety has dimension 0. And then this means if it has a dimension 0 and it's quasi-compact, then there are only finitely many solutions. Well, I mean, but for me, another conjecture was important, the so-called Tate conjecture. So Tate also was an Abel Prize winner. Well, for an Abelian variety, which is a group which has also which is a variety which also has a group structure. You can do this over finite fields, so they have only finitely many points. But you want to, well, I mean, there's a Galois representation. So Venus operates on the point in the algebraic closure, and there are endomorphisms, and the endomorphisms commute with the Galois operation, and the Tate conjecture says that the opposite is true. If you have something which commutes with the Galois representation on the so-called Tate module, then it comes from endomorphisms. And he found a method to prove this, namely, let's say you have a sequence of subgroups of the Abelian variety by itself, and then you look at the quotients, and you want to show that infinitely many of them are isomorphic, because then you somehow find morphisms between them, and this gives you endomorphisms. And in principle, this idea is clear, because they should be parameterized by some moduli space. And over a finite field, it has only finitely many rational points, and so there should be only finitely many isomorphism classes coming out of this procedure. So many of them are isomorphic, but the problem was this is true for so-called polarized Abelian varieties, and Tate had to really struggle to get rid of this. But then after this, there was a big simplification by Sahin, who proved that the height of there's some height function that the height of the quotient is constant, and so there again, because of the fundamental property of the height, that if it's constant, there are only finitely many of them. Okay, so this was a well, then we come to the 1970s. So there was Arkhelov. He generalized Parshin's results to curve with bit reduction. And also in 1974, he invented Arkhelov theory. So the idea is if you're over function fields, then out of the curve you get a surface, phi but over the base. And for number fields, I mean, you can do the same. You can take as the base the integers, and you have a relative curve over this. But then you are missing something. I said, I mean, you usually have to do projective spaces, and there you have to add points at infinity. And for number fields, there are no points at infinity, but there are sort of things. I mean, the points correspond to norms or p-adic norms on the integers, and there's also the real norm, and this gives you, well, this should replace infinity, and Arkhelov had the idea of using this, and the idea in Arkhelov theory is simply that you put metrics, real metrics on everything, and then study this. I mean, metrics are not as good enough as a usual algebraic structure, but you have to use what you get. Well, and then he was expected to prove Mordell, but I think he had difficulties with his health, and so this was left open. And then there was I had the good luck to meet Spiro, which was a friend of my advisor, Nastold, and he tried to extend Parshin's result to curves of positive characteristic. And well, if you are in positive characteristic, then Mordell cannot be true, because usually if you have a curve you can apply Frobenius, and this gives you infinitely many points. And he had to do this, and he had to eliminate Frobenius by the so-called Kodaira-Spencer class, which meant that the curve is sort of non-constant or non-isotrivial. Okay, and now I can finally talk about myself. In early 1980, I visited Paris and talked to Spiro, and he lectured me about Arkhelov theory, and I found this very interesting. And because as a young guy, you are either looking for promising fields to work on, and so I did this. And then, first of all, I extended the Parshin-Arkhelov methods to families of abelian varieties, our function fields. It was a surprise. I mean, as I said, to prove finiteness this way, you have to prove that the things are parameterized by an algebraic variety of finite type, and then you have to prove that points cannot be deformed, so that it's zero-dimensional. And I could prove the first half, that there's some finiteness of invariance, but for the second one, things could be deformed. Well, and I must say one thing which helped me. I wanted to have a height function for abelian varieties, and in principle of a function field, this is related to giving an ample line bundle on the modular space of abelian varieties, and then you get a height function. And in the function field case, there is a canonical ample line bundle which is given by the top differential of the universal abelian variety. And so I could use this. And there was an interesting episode because the referee suggested to replace the arguments with arguments from hyperbolic geometry. That sort of things into hyperbolic spaces are bounded, but I didn't know this, and I refused to change it. So I worked with the omega. And also, being talking about moduli spaces, I knew that they existed, but there was a complicated construction of them, and my impression was always that people were exhausted after constructing them, and they wouldn't use it for anything useful. But then this became, I learned that this was not true. There was a Arbeitsgemeinschaft in Wolfach, which means people talk about some hot topic, and there was a work of Harris Mumford, and they sort of showed me how to work with modular spaces. So I lost my respect for them. Well, and then back in Germany, I thought about the Tate conjecture. And as I said, it means essentially you take an Abelian variety, you divide by the steps of a p-divisible subgroup, and you want to prove that many of the quotients are isomorphic. And, well, I mean, first of all, needed a height function for Abelian variety, but this was now obvious because for the height function, you should choose the omega on the modular space, and you would have to put a metric on it. But this was also not difficult. You could just take the square integration over the Abelian variety of a form. And so I thought this was obvious, what to do. And but then I had to think, I mean, you take the quotient, and if you have the quotient of an Abelian variety, you have a map from A to B. And what happens to the heights? There are sort of two terms, which one thing is if you go to B, you integrate over a quotient, and so the integral is smaller. You get something like the square root of the degree because it takes the L2 integral. And then other effect is that, I mean, you have to take a generator of the integral differential forms, and then this also goes, well, also the generators, well, the generators are bigger. I mean, let's say, I mean, you have a generator for A, which is alpha, and then for B it might be only 2 alpha or 4 alpha or 3 alpha or something like this. So if you do the square integral, it would go up. And so then I had the good luck that these two effects tended to cancel. There's a reason, I mean, there was work of Tate about relation between the differentials and the Galois representations. And there was the classical work of André Weil that the Galois representation have sort of pure of, I think it's called weight 1, which means that the Frobenius has eigenvalues square root of p. And these things just give you that, I mean, the square root gives you a factor 1/2, and you said you have the degree to the power 1/2, and the degree also comes in if you divide which group you divide. So this way, I got the Tate conjecture, and then I talked in Wolfach about this, and when I came back, I found also that you could do more, because there were theorems of Renault about isogenies if you don't divide by the steps of a p-divisible group, but just by a finite group scheme. And I put this together. I got finiteness. Well, I got that in each isogeny class of a Abelian variety. There are only finitely many of them. And then I also proved finiteness of isogeny classes by using an argument about the Weil conjecture that the Frobenius have certain absolute value. And so if you like to, I mean, we didn't have a Kodaira-Spencer class, but the Galois representation did the job. I mean, this is this time maybe it wasn't. I didn't realize it, but then now there are new proofs of Mordell which use, don't use the height functions, but use Galois representation. By the way, the height functions are these called Faltings heights. On what I tried to say, that it was obvious what to do, but it shows, sometimes you get credit for things which were easy, and sometimes you don't get credit for things where you worked hard. Well, and then there was a new thing which I said that Vojta managed to use Diophantine approximation to prove Mordell. Well, he was the first guy. Well, there was a theorem of Mordell, which was a generalization of Mordell's theorem, that the rational points form a finitely generated Abelian group. And as I said, nobody managed to go on from this, except Vojta. What he did, if you have a finitely generated group, it's like a vector space, and he looked at solutions sort of in a certain cones in this vector space. So if you have a vector space, you can write this as finitely many cones, and in the cones, sort of the points have the same direction. And then there was an old argument of Mumford that then they would have to increase rapidly. But then you use the sort of root theorem type arguments to show that this could not happen. Well, and I got involved. People told me that it was a nice thing. Maybe they just were happy that they didn't have to hope to quote Faltings anymore. But nobody seemed to be quite willing to say that it was correct. And then I said, well, I should look into this. And so I tried to do a good deed, but I was rewarded, because then I found not only that it was correct, but that it could be done in more generality. And finally, I also understand how to prove the complicated Roth lemma. And there are recent results now with p-added periods domains. There's a new proof by Lawrence and Venkatesh. They use they use a variant of the Parshin Kodaira construction to map the curve to a certain parameter space for Galois representation. And then they prove that the image of the curve is Zariski dense, and then that the Galois representation lie in a proper subspace. So this is why I have a patent for this, because I proved finiteness of Galois representation, so they could not quite get rid of me. But then they proved, because it's a proper subvariety, it lies in a hypersurface, and because the image of the curve is dense, then there are only finitely many points. And on the other hand, there are things, there are new developments about bounding the number of points. Well, that's not really the thing you want. You also want to bound the height of points, but nobody knows how to do this. And this is done by, there are now new results. For example, they could treat the famous, what is it called? The cursed curve. That's a curve which is a modular curve, which you need to prove some conjectures. and they wanted to prove finiteness, and all the methods which were known just didn't work. For example, the Roson method is a so-called Chaboty. If the rank of the Jacobian is sort of smaller than the genus, then it's okay. But then I think for this curve it was just one off, and so it didn't work. But they could give it the so-called cursed curve. Okay, I'm finished. I'm 26 seconds over, but I think that's acceptable.
Thank you very much, and we have time for a couple of questions, if there are any questions or comments from the audience.
So thank you for the very elementary lecture. So,
Yeah.
so I have two questions. So the first question is that the Mordell conjecture is about curves of genus at least 2. So where does this condition about higher genus actually come up in the proofs? And then the second question is about, so some of these curves are known to have no non-zero integral solutions like Fermat curves.
Yeah.
And is there a way to somehow, I don't know, somehow at least conjecturally to categorize these curves which you don't expect any integral solutions except for 0?
Well, I mean, the difference between me and Fermat is in Fermat it's only over rationals, but then it's strictly, no solutions or only the trivial solutions. And the Mordell, it goes over arbitrary number fields, but it gives you only finite dimensional solutions. And to bound the number of solutions is sort of difficult. Usually you need the rank of the Jacobian, and there are so-called small points and big points. And big points, I think you can use Vojta's method. They lie in finitely many cones, but for small points you have to do something else. So there are people doing this, but as I said, what you really would want is to bound the height of the points and so-called effective model, and nobody has an idea.
So you didn't answer my first question about genus. So why did Mordell conjecture, Mordell's conjecture is about curves of genus at least 2?
Yeah.
So where does this higher genus appear in the proof?
The higher genus appears that, let's say you have the Skodira Parshin construction. You choose a point, you want to find the covering which is only ramified at the point and characterizes the point. But if in an elliptic curve it's homogeneous, all points, for each 2 points there's an isomorphism between them, and then the construction also would give the isomorphic curve points.
Okay, thank you.
Yeah.
Thank you. Are there any further questions? If not, let's thank Professor Faltings once more.